Okay, good afternoon, dear participants. I'm glad to welcome everyone to this afternoon session of the conference. And we are beginning with the presentation by Yevhenii Chapovskyi on Lie subalgebras of SL3R revisited. Yevhenii, stage is yours, please.
Good afternoon, dear colleagues. First of all, I would like to say thank you very much to the organizing committee for making this conference happen, especially in our troubled times. Next, I would like to present the results obtained jointly by Sergei Koval, Olga Zhur, and I concerning the problem of Lie subalgebra classification, mainly in the case of special linear Lie algebra of rank 3 over the field of real numbers. Let us proceed with the general problem statement. Consider a connected real Lie group and the corresponding Lie algebra. It is said that Lie subalgebras H1 and H2 are conjugate if and only if there exists such an element of the Lie group that the corresponding joint operator maps H1 to H2. And our problem is to classify all conjugacy classes of Lie subalgebras of the Lie algebra G for the given Lie algebra. Next, I would like to briefly mention several major applications of this problem. The first application is the classification problem of invariant solutions of a PDE. And an example is given concerning the case of SL3. The next application is the classification problem of normal linear systems of second-order ODE. Yet another very important application of this problem is the problem of classification of all realizations of Lie algebra. Finally, I would like to mention that the classification of subalgebras of the Lie algebra are very useful for the study of graded contractions of Lie algebra. Our ideas, approaches, and algorithms are mainly inspired by the work of Winternitz, subalgebras of Lie algebras, example of SL3. It is, to the best of our knowledge, the most successful attempt to provide the subalgebras classification for SL3. It contains many bright ideas and methods, but it's not completely satisfactory either. First of all, although it is surprising how few mistakes there are, especially considering the volume of computations, there are still mistakes that are to be corrected. Further, the theoretical part of the paper contains emissions, and there are many proof and computation missing altogether. We have tried our best to make up for these flaws. Next, proceed with general scheme provided by Winternitz. First, assume that G is a linear Lie algebra. We can always do that. Then either G can be decomposed in a semi-direct product of some subalgebras. In this case, we can apply algorithms given below to reduce the problem of subalgebra classification for the whole Lie algebra G to the same problem for its summands. Otherwise, we can conclude that G is a simple Lie algebra, and then we can find its maximal Lie subalgebras, apply the scheme recursively, merge the corresponding systems of representatives of each maximal subalgebras, and then clean up redundancies in the resulting list. For more details, I would like to refer you to the paper. Also, I would like to mention that if the dimension of the Lie algebra is greater than 4, in order for computations to be manageable and for us to have a nice framework to work with, the additional constraints are needed. We consider two cases. First, the semi-direct product is actually a direct product of Lie algebras. Second, the second summand G2 is an abelian Lie algebra. Let us proceed with the second cases. These two cases are pretty similar, and moreover, the second one is the one we actually use for the classification problem of SL3. So let us proceed with the next proposition. Let G be semi-direct product of G1 and G2, and G2 be an abelian Lie algebra. This proposition gives us a bijective correspondence which maps any Lie subalgebra H of semi-direct product G1 by G2 to the triple H1, U, and alpha, where H1 is a subalgebra of the first summand G1, U is H1 submodule in G2, and alpha is a cocycle from H1 to the factor module G2 by U. Let us recall that a cocycle of Lie algebra in a module over this Lie algebra is a linear map satisfying the following equality. Yes. The proposition gives this map explicitly and in its inverse explicitly. In this way, instead of classifying the subalgebras of G, we can classify the triples up to the corresponding action. In this way, we have the following algorithm. First, we construct representatives, each one of the conjugacy classes with subalgebras in G1. Then, for each representative H1, we construct representatives of submodules up to the group of all elements which do not move the representative H1. Then, for each pair of representatives H1 and U, we construct representatives of cocycles up to the group of all elements that do not move both H1 and U1 with the following action. And then for each triple H1, U, and alpha, we recover the corresponding Lie subalgebra H according to the previous proposition. It is worth to mention that if we look at the action of group elements on cocycles alpha, we will see that if J is an identity, this action corresponds to cohomological equivalence between cocycles. And we actually briefly make use of this fact by using Whitehead's lemma in one of the cases. Next, let us apply the previously mentioned algorithms to the case of the special linear algebra of rank 3. Below, we give the basis we are working in. It's a pretty natural basis. E1, E2, E3 make the basis of SL2. D completes it to the basis of GL2, and P1, P2, and R1, R2 further complete it to the basis of the Lie subalgebras A1 and A2, respectively. SL3 is a simple Lie algebra. So first we have to find the maximal Lie subalgebras. Since it is a linear Lie algebra, we can categorize its maximal Lie subalgebras depending on the dimension of the corresponding invariant subspace. If subalgebra of SL3 has no trivial invariant subspaces, then we will call it irreducibly embedded subalgebra, and it is shown that SO3 and SO21 are the only irreducibly embedded maximal subalgebras in SL3. Winternitz asserted this fact, and we have reproved it. If a maximal Lie subalgebra has a non-trivial invariant subspace, then it has either dimension 1 or dimension 2, corresponding to the subalgebras A2 and A1 respectively. Both the subalgebras are isomorphic to rank 2 real affine Lie algebra, which is conveniently isomorphic to the semi-direct product of GL2 by R2, allowing us to apply the previous algorithm. The next few slides contain the explanation why SO3 and SO21 are the only irreducibly embedded subalgebras. Those are pretty easy statements of representation theory, so I will skip them for now. I may return to them if enough time will remain in the end. And next, let's proceed with the interesting part, cleaning up the redundant subalgebras. In the paper of Winternitz, there is no mention as to how this cleaning up have to be implemented, so this part is completely original. Proposition. Let M be a Lie subalgebra in G. M capital, the corresponding Lie subgroup in G. Let us choose some subset C in G in such a way that any element of G can be written as a product of an element of M and an element of C. We can always find some subset C. For instance, we can choose the whole Lie group G, although it's not a very productive choice, of course. Then, Lie subalgebras H1 inside M and any Lie subalgebra H2 are conjugate if and only if there exists such an element G in this complementary subset C, such that the corresponding adjoint operator maps H2 inside M, and moreover, this image is equivalent to H1 inside M. In this way, we can perform this verification in 2 steps. And the second steps already assumed to be known, because this is a proper subalgebra inside G. So the crucial step is to find such an element of the complementary subset that the image lies in M. And when we go from the list of affine subalgebras up to the affine Lie algebra, to the list of affine Lie subalgebras, but up to FL3, only the first step is crucial. So how do we find such complementary subset? In general, it is quite natural to consider complement subspace to the Lie subalgebra M, and then to consider the exponent. From the notion of canonical coordinate systems, we obtain some chart in identity, and by left or right multiplication or by some elements of G, we can move this chart to the whole Lie group G. In general, we can only be sure that we can choose some at most countable union of such charts. For compact Lie groups, obviously, we can choose a finite cover. Otherwise, we can only proceed by case basis. Next lemma provides this complementary subset for FE3 for subgroup H, which correspond to the Lie algebra A1. As we can see, it's only a 2-parametric subset, which is pretty good, if I say so. In this way, applying the lemma given above, we can efficiently clean up the list of A1 in equivalent Lie subalgebras up to FL3 in the following way. For each subalgebra S in the list, we find parameters I, C1, and C2 such that the image of the corresponding action lies in A1. And then, using the previously stated algorithm, we find the corresponding representative in the list. Next, I would like to show you the main result. This is a complete list of proper SL3 inequivalent subalgebras of the special linear Lie-algebra of rank 3 for the field R. It contains uh, 3 dozens of subalgebras, almost 40 actually. And it is quite similar to the result obtained by Winternitz. There are several minor mistakes. In dimension 1, a family is incomplete. In the dimension 3, a pair of subalgebras are conjugated in Winternitz classification. A pair of families are incomplete and one subalgebra is missed. And the cases of dimensions 5 and 6 contain several misprints. Sergey, please tell me how much time do I have?
Well, almost finished.
Then I'll just give a few remarks. The algorithm is pretty clear and efficient, but if we multiply the number of Lie subalgebras in a fine Lie algebra, something like 30 subalgebra, multiply by these 3 parameterized matrices, we obtain 90 cases. In each case, if there is a non-trivial intersection, we need to find the canonical representative. So it's pretty clear that there is a huge load of computations, which are very difficult to write and even more difficult to verify. So I'm not surprised that Winternitz didn't want to include all these calculations in the paper. That is given pretty efficient algorithm, and I'm not sure how he did this verification step. So we have decided to write a notebook in Python where we include these computations by using symbolic computation software in order to further assure ourselves that our results are correct. And since the time is up, that's pretty much it. Thank you for attention.